Hello everyone, this is Dr. Young, and in this video we're going to talk about the reduction of carbonyl compounds but using alkyl donors this time instead of hydride donors. Basically the only difference in this video is that we're going to be adding basically the equivalent of an R- instead of an H-. So let's take a look at the reagents that'll do that. The two big ones that we're going to talk about right now are the organolithium and the Grignard reagents. These Grignard reagents are sometimes also called the organomagnesium. So organomagnesium. Because they have magnesium in them. The organolithium and the organomagnesium, these Grignard reagents here, they are both considered what we call organometallic reagents. So organometallic. The name should be fairly obvious, right? It's just that you basically have a carbon-metal bond in them. And later there's a whole chapter that we'll cover called organometallic reactions. Those are just reactions that involve, at some point, a carbon being attached to a metal. It's not a super common thing out in nature, so it's kind of, they have their own special name for that reason. We'll see later that organometallic reactions are super, super important. These are good. These reducing agents are good. They're very useful. They find themselves a lot in sort of research labs. But the palladium catalyzed cross couplings and nickel catalyzed cross couplings are enormous reactions. People have won Nobel Prizes for them and stuff. So we'll come back and talk more about organometallic reactions later. But right now I want to look at these two in the context of reducing carbonyls. So let's take a little closer look at the structure of these. I'm going to use, as an example, I'm going to do CH3Li, so just methyl lithium. So for methyl lithium, we'll draw this little sucker out. And for Grignard, I'll use a methyl group for my R group for Grignard too. And I'll put magnesium and then X. Remember that X is for halogens. So really you could do any halogen you want. I can't remember ever seeing fluorine being used, but chlorine, bromine, and iodine are commonly used. Bromine's probably the most common one, but I'll put chlorine for this example just to have an example. And let me draw out the structure for this Grignard reagent. So now what I want to mention here, right, the reason why I'm drawing these out is, well, one, to show you the covalent bond between the carbon and the metal, the lithium on the left, magnesium on the right. But I want to emphasize to you that while they're covalent bonds mostly, they are darn near ionic. So if I take a look at this carbon here, right, and if I look up the electronegativity of carbon, I see that it's 2.55. And you may have a different table. I mean, these electronegativity values might vary depending on who did what research, but around 2.55. And if you take a look at lithium, it's going to be around 1.57. And if you just subtract those, you get a difference in their electronegativities of 1.57. And if that doesn't mean too much to you, just keep in mind that 1.7 is considered ionic. So we're almost to 1.7. We're getting real, real close to ionic. Or in other words, one thing that we can say here is that, when I put up my partial charge, because this is like, you can think about it as a very, 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 very polar bond, or like almost ionic. And so for these charges, I'm just going to put a huge delta plus and a huge delta minus. It's almost like a C minus. And then same thing over here on the right-hand side, carbon's still 2.55. This magnesium is not nearly as electropositive as lithium. It's more like 1.3. But still, if you look at the difference in electronegativities here, you get 1.24 for that bond. So it's still a very polar, almost ionic bond. So delta plus, delta minus. These things have large differences in electronegativity. And I'll mention this again later, but when we talk about the palladium catalyzed cross couplings later on in a different chapter, we'll see that palladium and carbon have all a very, very, very small difference in electronegativity. They're almost nonpolar, which changes the reactivity like crazy. So what we're going to do is we're going to treat these organolithiums and organomagnesiums as more or less being a carb anion, right? So I'm going to put it in quotes, right? We're going to treat it like they're anions there, because they behave basically like it. They behave basically like nucleophiles at those carbons. And since we have more or less a negative charge or almost a negative charge on these carbons, you can imagine that these are going to be really, really, really strong nucleophiles. So both of these here, I'll just put it in the middle, both of them are very strong nucleophiles, because you basically have a negative carbon, and also both of them are very strong bases, right? Because you don't want a negative just sitting around on a carbon. So these are very, very strong bases. And in fact, the organolithiums, like T-butyl lithium or methyl lithium, those are some of the stronger bases that we have available to us in the laboratory. So they're extremely strong bases, very, very strong bases. And since they're really, really strong bases, you can imagine that I need to be very careful about my solvent choice and what other reactants are around, right? So because they're very strong bases, I need to avoid anything even remotely acidic. I can't have anything even remotely acidic around because they will just do an acid-base reaction with that instead. So avoid acid-base reactions, right? So this means no alcohols, no water. You have to make sure all your glassware is super dry. No water, no amines, right? So nothing with nitrogens and hydrogens. Anything even remotely acidic. No alkynes, no terminal alkynes. Anything even remotely acidic, these will deprotonate and you won't have them reduce your carbonyl. So you got to be careful of that. So what solvents do you choose? Kind of like those same solvents that we used with the lithium aluminum tetrahydride in the previous video. That was also a strong base. And so we're going to use the same thing. So we need to use ether solvents. Right, we're either going to have something like THF, which again is tetrahydrofuran, which is this little guy, or we're going to have diethyl ether, usually written out ET2O, which is our little bat friend, right, the diethyl ether, because ether solvents, they're not acidic, they don't react with really anything except acids, these are strong bases, so we're in the clear. So usually you see these used with THF or diethyl ether, and again, for either one. What are we going to use these for? Right now, we're just going to use them to react with aldehydes and ketones, but really they can work, they do work with any carbonyl. So these react with any carbonyl. Any carbonyl compound. So it's not like we don't have a weak version here where like, oh, only one of them works with aldehydes and ketones. Both of these will work with any carbonyl compound. So this includes, right? So this includes things like esters and amides, etc. I'm not going to show you any reactions with esters and amides in this video. We're still just talking about aldehydes and ketones, so I'm going to focus on aldehydes and ketones here. We will see later in the carboxylic acid derivative chapter that we'll react these to esters and amides and things like that. How do we make these reagents? These reagents are made basically from some sort of alkyl halide. So I'll leave this generic as just an R group. So let's just say we have some whatever X, bromine, chlorine, something. And the idea for the organolithiums is you add 2 equivalents of metallic lithium. So I put a little 0 up there to indicate that the oxidation state is 0. Or I could put in parentheses that it's a solid. Right, so we're talking about not lithium ion, not Li+, it's Li0. It's actual metallic lithium. And then that's going to give you your organic piece with the lithium attached to it now. And then you're also going to make a salt, the lithium bromide, lithium chloride, lithium iodide, whatever X was there before, whatever halogen was there before. To make the organomagnesium ones, to make the Grignard reagents, it's kind of the same thing. You just don't need 2 equivalents. So you take your HX, you just add magnesium, and I put that 0 because it's like magnesium turnings or ribbons or something like that. You actually add metallic magnesium, and that just inserts itself in between the halogen and the alkyl group to give you your organometallic reagent. How does it insert itself? Don't need to know the mechanism right now. It's actually an oxidative addition, but that's not something that you need to know. We'll talk maybe a little bit about that when we do organometallic stuff. So those are the 2 reagents. More or less, they're really, really, really equivalent. They're both extremely strong. They both donate 1 R group. The Grignard reagents, though, the organomagnesium ones, the ones on the right, that's the one that's really a lot more common for reducing carbonyls because they're a little bit easier to work with. They're not quite as dangerous. They're easy to make. The organolithiums are great, but oftentimes we use those more for like really, really strong bases, and they have the problem of being really, really flammable. If you just shoot, you have to be careful of not letting them touch the air because they'll catch on fire, and a lot of people have hurt themselves and some folks have died mishandling those reagents. So Grignard reagents are used more often than the organolithiums are. So quick look at the magnesium, the organomagnesium mechanism here. Both of these are going to be really, really, really similar. So let's just say we have some carbonyl. Got this methyl ethyl ketone here, or the 2-butanone. And so we'll see something like, for example, let's just say I'm going to have a lot of propyl, MgBr, and I'll say it's in THF. And then step 2, I'm just going to pick an acid workup, let's say bisulfate, sodium bisulfate, or again, any remotely acidic thing would be fine. All we're going to do for these, let me make this look more like what I drew up there, MgBr. What we're going to do is, again, you treat them kind of like it's ionic. So I'm just going to draw this over here as saying, like, we're treating this like this is an ionic bond. That's how you want to think of it, is that this is kind of like being ionic. So it's that carbon right here that's super negative, and this magnesium is quite positive. It's that carbon bond, that carbon-magnesium bond that's going to be the one that breaks and attacks the carbonyl. So what we draw for the mechanism is that from that bond, so those 2 electrons in that carbon-magnesium bond, those are going to be the ones that attack the carbonyl, right? Because if you look at the carbonyl, just again, like in the last video, that's the partially negative spot, that's the partially positive spot. So we have the nucleophile attack that electrophilic carbon and the carbonyl carbon. But that carbon can't have 4 bonds, right? It can't have 2 to the O and 1 to the methyl and 1 to the ethyl and a new 1 to this propyl. Something's got to give. What gives the weakest bond, which is the pi bond. So from there, we just draw the first intermediate, which was this. So now we have O minus. And I've just added a 1, 2, 3 carbon piece. So 1, 2, 3 carbon piece. That's the new piece right there, right? If I label these carbons 1, whoops, come on. Why does this happen? Sorry, I'm having a pen malfunction. 1, 2. Ah, that's weird. Let's try this again. There we go. Thanks for bearing with me. I'd say I'm going to edit this out, but I'm not going to. 1, 2, 3, carbon 1, 2, 3. This is carbon 1, 2, 3, right? So I'm going to keep track of my carbons. I don't want to lose carbons. It's very, very easy for students, for me, to lose carbons when you're doing these reactions. So that was all the stuff that happened in step 1, right? You added your Grignard reagent to your carbonyl, and then that you just sit at this alkoxide here. And so the alkoxide is just going to sit there, la-di-da, until you do your second step, your acid workup step. And so in this case, again, we just have the thiosulfate. So our last step, and again, you could use a lot of different acids. Ammonium chloride is also really common to protonate your product to give you the alcohol. So OH, like that. You can draw that. That's totally fine. This drawing kind of bugs me. For some reason, I much prefer this. It's the same thing. It's just kind of straightened out a little bit. But the idea is that I made a new carbon-carbon bond, which is one of the big important things here. Before, I think the only way you knew how to make a carbon-carbon bond, actually you knew 2. One was with alkynes, terminal alkynes, deprotonating them, making them a nucleophile. The second was the Friedel-Crafts alkylation and acylations. Those were the only ways that you knew how to make carbon-carbon bonds in the past. This is a new way, and so it's very important to note that this is a new carbon-carbon bond that you made. And so when you start to do more synthesis problems and all of a sudden you have a larger molecule with more carbons, you want to start thinking, it could be one of these organometallic things, these Grignard reagents. I'll do an organolithium one real quick, but it's basically the exact same thing. All right, so maybe step 1, let's do a phenolithium, and I'll do a diethyl ether this time. Step 2, maybe I'll use ammonium chloride. And so if I have my phenyl lithium, it's all the same logics, right? Actually, maybe you should pause right here and take a stab. It's not going to be anything different here. So your nucleophile, your reducing agent is going to attack the carbonyl. You're going to get your first intermediate, which is that alkoxide. Whoops, so it's still O minus here. I'm going to draw my phenyl ring. New thing that I added. There was a methyl on there still. That's an O minus. And then again, your second step stuff is just to add the H so that you get your product. That's terrible drawing. I'm going too fast because I'm feeling impatient. I feel a lot of pressure to make these videos really, really short for you all, even though I don't like rushing through these things, but everyone says that you can't make a short video, you can't make a long video on YouTube. So that would be your product, right? So all I really did in that last step was protonate the alcohol to get your product. So here's product one, here's another product. Where you put in space the phenyl versus the methyl versus the ethyl doesn't matter. As long as they're attached in the right way, you're good to go. So don't get too hung up on, well, should it be on the left side or the top side or the right side? That doesn't matter at all. So the mechanism is very, very straightforward, very simple. Some examples. So I'm going to do the first couple, and then I'll pause and let you do the rest. So all you do, right, you just need to look at the carbon piece that you're adding. So for me, I see that it's a 2 carbon piece, so it's an ethyl. And I know that I'm going to add it, right, to my carbonyl, delta minus, delta plus. So I know that my ethyl is just going to attack this spot and kick those up, and I'm going to be left with the alcohol at the end. So all I need to do is draw my cyclohexane. I know there's going to be an alcohol, and I know there's a 2 carbon piece here. I added an ethyl. So there's my 2 carbon piece. And that's really it. That's all you have to do. Right? So again, if this was carbon 1 and 2, this is carbon 1 and 2. Those are the ones that I added. Same thing for the bottom one. It looks like I'm adding a phenyl. So I've got the pH there. That stands for phenyl. So that's just the benzene ring with no extra stuff added to it. And again, I'm going to add it to that carbonyl carbon here. So partial negative, partial positive. I know that that's going to go and attack there, kick that up. So I can draw that product. OH, I'll make that the ethyl, this a methyl, and I'll put the phenyl on here. Oh, look, it's the same product as that other one. So I've got that product. And then I think that this would be a good place for you to just pause for a minute, try these last 4, and then we'll finish them up together. So take a minute. I'll stop talking. All right, so hopefully you paused and took a crack at these so that your brain can do some thinking. For this last one, we just have an OH and then a new methyl. This one's supposed to be kind of tricky. If you don't see excess or true equivalents, I would just assume that things are a 1 equivalent, which means that we have a problem here because this ethyl group is not going to react with my carbonyl. There's an OH here. And so really what it's going to do is it's going to deprotonate the OH to give you this. Right? It's just going to deprotonate that sucker and give you ethane, which then evaporates away. And then you would reprotonate it with your ammonium chloride. So you would either write for this either no reaction because nothing net is going to happen, or just that you're going to get your starting material back. You're just going to reprotonate that negative oxygen with the ammonium chloride in step 2, and it looks like nothing happens. So you want to be mindful, again, remember that if an alcohol is around, 1 equivalent of this stuff is going to get chewed up by that alcohol because it's just going to do an acid-base reaction, kill your reagent. The way we work around that is we add 2 equivalents, like in this second one. We add 2 equivalents so that 1 equivalent, the first equivalent, is going to go deprotonate that alcohol, but then we have a second equivalent that can then attack the carbonyl to give us the product we want. And then when we work it up, we just reprotonate the things again. So now, let's see, there'd be an OH here. I added an ethyl group and a methyl group, right? So that this would be my ethyl group right here. Right, that would be the ethyl piece that I just added. 1, 2, the 2 carbons that I added. So if you do have an alcohol somewhere on a molecule and you need to still reduce an aldehyde or ketone, you can add multiple equivalents. Just know that your first one's going to do an acid-base reaction because acid-base reactions are so fast that kinetically they're very, very, very quick. So that's what's going to happen first. And then the reduction of the carbonyl will happen second. And then lastly, in this one, here's an example of a vinyl Grignard reaction. So we have a MgBr hanging off of an alkene, which is totally fine. And then this is just going to attack that carbonyl to give us this alcohol. That's how we use those organometallic reducing agents on carbonyls. Organolithium, organomagnesium. For the most part, we treat them the same. Technically, the organolithiums are a little bit more basic, a little bit hotter of a reagent, but the Grignards are really, really, really common. Those are the more common ones. So study up, practice. Good luck. If you have any questions or comments, you can leave them down below. Thank you.